Good morning, everybody. Welcome to today's session. In the previous session, we looked into the complex circuits. And what is a complex circuit? Complex circuit is a circuit where you cannot identify whether the resistors are connected in series or parallel. And also there will be usage of multiple EMF sources. So that way it will become by just looking at the circuit diagram, we will not be able to tell whether it is connected in series and parallel. Such circuits are called as a complex circuits. So already we have seen simple circuits. Simple circuits are where you can easily identify whether it is series or parallel, and you can apply the Ohm's law, and you will be able to solve simple circuits. To solve the complex circuits, will be using the Kirchhoff's law. And Kirchhoff's, he has provided two laws, one for the current, one is called as the KCL, Kirchhoff's current law, and Kirchhoff's voltage law, that is KVL. And what is Kirchhoff's current law? In any electrical node. So if you have a big electrical circuit, in any node, the incoming currents is equal to sum of incoming currents is equal to sum of the outgoing currents. So you can see here I1 and I3 are incoming currents. They are coming towards the node, and these two currents, they are going away from the node. I2 and I4, those are called as outgoing currents. So because it is a DC current, it has a definite direction, right? So if according to the Kirchhoff's current law, the algebraic sum of the current entering the node is equal to the algebraic sum of currents leaving the node in an electrical circuit. Or you can also define it as algebraic sum of the currents meeting at a junction or a node in an electrical circuit is zero. Whichever is easy for you to understand, you can memorize. So how to apply the current law? At node A, sum of incoming currents is equal to sum of outgoing currents. Incoming current I1 plus I3 is equal to I2 plus I4. And if you take I2 plus I4 on the left hand side, it will become I1 plus I3 minus I2 minus I4 is equal to 0, which is nothing but the second statement. Kirchhoff's voltage law. Uh, Kirchhoff's current law is applied to the node, electrical node, any node in the circuit, and Kirchhoff's voltage law is applied to a closed loop or a mesh. Okay, and what is the how we state the Kirchhoff's voltage law? In any closed electrical circuit or mesh, the algebraic sum of all electromotive forces, EMF sources, and voltage drops in resistors is equal to 0. That is algebraic sum of all the EMF plus algebraic sum of all the voltage drops is equal to 0. That is sigma EMFs plus sigma voltage drops is equal to 0. Then we apply to this simple circuit. And when we are applying the KCL and KVL, what is the first thing we need to do? First thing, irrespective whether it is given or not, we have to make sure that first you mark all the nodes. Okay, so in this case I would say A, B, C, D, and if there are in this particular simple circuit we have only one loop. If there are many loops, you name the node according to that, then put the direction of tracing. And as I told you, our convention is we are going to take the direction of tracing as clockwise and mark all the currents. Okay, here there is only one loop, so only one current. If there are two loops, there will be two loop currents, and so on. And once you mark that, then according to sign convention, we will apply the Ohm's law and apply the KVL, Kirchhoff's voltage law. And one more convention we have to follow is whenever we are tracing, I told you, so we are going to apply the KVL to a loop A, B, C, D, and A. When we are applying, this is the direction of tracing, and we have to follow this sign convention. For EMF sources, what is the convention? When you are doing the tracing, and if you come across the positive plate, then you take this voltage as a plus. Okay, if it is 50 volt, you will take plus 50. And whenever you are doing the tracing and you come across the negative plate of the EMF source, you will take this voltage as negative value. Suppose if it is a 25 volt, you will take it as minus 25. Similarly, the convention for the voltage drops. Convention for the voltage drop, if the direction of the tracing and direction of the current, if both are same, the voltage drop across the resistor, that is I into R, is taken as positive value. And if the direction of tracing and the direction of current are opposite, then you will take the voltage drop across the resistor I into R as a negative value. So that is the convention we are going to follow. For simple circuit, what we have done, we have identified all the nodes A, B, C, D. We mark the nodes, then we mark the direction of tracing, then we mark the current. Once we have all this, we will apply KVL to the loop A, B, C, D, A. Okay, we start from the node A and we come across the resistor. Now the direction of tracing is in this direction, and current direction is also in the same direction. This voltage drop is going to be positive. And what is the current? Current is I into R1. I take it the positive sign. And when we come to this resistor, the direction of tracing is like this, and the direction of current is also in the same direction. So this voltage drop I into R2 will be again positive, plus I into R2. Then while tracing, we come to the node C, D, and if you see, we are coming and hitting the negative plate of the voltage source. I will take it as a minus value, minus V, and come back to the original node. We are done with all the components, equal to 0. So this is the resulting equation by applying the KVL to this particular circuit. So this we get it as IR1 plus IR2 is equal to V. So this circuit, I think I have given it as a homework. This is a simple circuit. We can do it using the Ohm's law. Okay, and what we have to find, current. So current is only one current here. So that's why this particular resistor is connected in series with this resistor. So 2 plus 5, 7 ohm. And if you see, the 30 volt EMF source is trying to push the current in this direction, while this 10 volt source is trying to push the current in this direction. Effective voltage would be 30 minus 10, that is 20 volts. So it is as good as a 7 ohm resistor is connected to 20 volt EMF source. So it's a simple circuit. We apply Ohm's law. V is equal to I into R. So we know V is 20 is equal to I into 7, or I is equal to 20 by 7. Now, that is the 20 by 7, whatever the value you get here, 2.857. That is using the simple analysis. So in exam or wherever you get the circuits, you don't really worry about how the components are connected, series or parallel. If you are in a confusion, directly apply the KCL and Kirchhoff's laws. Okay, so let us apply the Kirchhoff's law. For this circuit, what we have to do, first we have to identify the nodes, mark the nodes A, B, C, D, then mark the direction of tracing, mark the currents. So that is what we have done. We have said A, B, C, D. The way you want to mark the node, it is up to you. There is no one specific way to do it. Whatever way you want to do, you can do it. And same for the direction of the current. You can choose any direction. If you have a doubt how to select the direction, select any direction. Okay, and if that direction is correct, you will get the answer for that current as positive value. And if that direction is not correct, you will get the answer for that current as a minus value. Minus value will indicate the direction of the current is opposite to what you have considered, okay, what you have marked. That's it. So nodes are marked, direction of tracing clockwise. Then the current, I know like 30 volt is higher than the 10 volt. I have marked the current in this direction. So current will flow like this and it will come back. Now we will apply the Kirchhoff's law. Apply KVL to A, B, C, D, A. So you put A also here. So that will make a complete loop. Then we start with the node A. So you start tracing from here. Now you can see the direction of the current is like this, and the direction of tracing is also in the same direction. And the current value is unknown. You mark it as I. 2 into I is the voltage drop across this resistor. So you will take it with the plus sign, plus 2 into I. Next, you come across the EMF source. So you are coming and hitting the positive plate. So you will take this value 10 volt as a plus value, plus 10. Then you come across a resistor. The direction of the current is like this, and the direction of the tracing is also like this. So this voltage drop is going to be positive, that is plus. And what is the voltage drop? 5 into I, the current. Current would be the same, plus 5I. Right? Then you come to the node C, okay, D, and you come and hit the negative plate of the CMF source. If you hit the negative plate, you will take this value as minus. That's why minus 30, and you come back to the node A. All the components are done, equal to 0. Equal to 0. Now, if you simplify this, 2 plus 5, 7, 7i, 10 minus 30 minus 20. Therefore, 7i is equal to 7i minus 20 is equal to 0, or I is equal to 20 divided by 7, 2.857 amperes. Any questions?
No, sir.
Okay, is it clear, right? Same thing we are going to apply for a little. This is a very simple circuit I have considered. A little bit bigger problem. For your exam, most of the time you will get 2 loops. Okay, and if the question paper is difficult, you might get 3 loops. If it gets 3 loops, then number of unknowns are more. Okay, so the number of calculations required is a little bit more. So go with the basic understanding and apply the same concept. Whichever the circuit is there, whatever we discussed so far, you apply the same concept. Now, so this is the circuit. Find the current for given circuit. Okay, so this is the circuit. Then first thing is what? Before applying the KVL, what we have to do? The first thing is mark all the nodes. Okay, so this is the node, this is the node, this is mark all the nodes. You say A, B, C, D, E, F. Okay, so all the nodes are marked. Then the direction of tracing should be marked clockwise. And you remember when you are choosing the direction of tracing, I told you I'm going with the convention of clockwise. When you are saying you are going to do the tracing in a clockwise direction for one loop, then you cannot change the direction here. For every loop that is present in the circuit, you have to use the same direction. So direction of tracing here is clockwise, direction of tracing here is clockwise. And once you identify, once you do the marking of the node and marking of the direction of tracing, the next step is mark the currents. Okay, you can start with here. You can say this current as I1. Okay, and it comes to this particular node. When this current comes to this particular node, it has 2 paths, means the current will get divided. If the current is, let's say, 10 amperes, when it comes to this path, it has this path and this path. So current will get divided. How it will get divided? We have to do the calculation. So I1 comes here, this side current you mark it as I2, and this side current mark it as I3. Okay, so then what will happen? This I1 is equal to I2 plus I3, and this current will come here. This would be I2 and this would be I3. So I2 plus I3, again it will come back as I1. I1 current will flow back here. So if you use this branch current as I3, then how many unknowns you have? I1, I2, I3, 3 unknowns will be there. So better than that, what you can do is you can apply the Ohm's law here itself. Okay, so that we can right away we can reduce one unknown. So how to do that? Excuse me. Okay, I1 is the current flowing here, and let us say I2 is the current here. What would be the current flowing here? I give you the current here. This 5 amperes is coming, and I will tell you 3 amperes is going here. How much current will flow in this branch? Again, once again, 5 amperes is coming here, and I am telling you in this branch 3 amperes is flowing. How much current will flow in this branch? Hmm? Are you understanding the question? Shifa, correct, 2 amperes. Okay, everybody, I hope everybody agrees with that. 2 amperes. Okay, so if 5 amperes is coming here and it will get divided, 3 amperes will go here. How much current will go here? 5 minus 3, that is the remaining current will go here. 5 minus 3 is 2 amperes. So that is by applying the Kirchhoff's current. Now I am saying I1 is the current flowing here, I1, and you have marking this as current I2. So in terms of I1 and I2, how much current will flow here? Please speak up. How much current will flow here in terms of this is I1 and this is I2? How much current will flow here? Anybody? Shifa? I1 minus I2, correct. Okay. So if this is the current I1 that is flowing, and if you mark this as I2, I1 minus I2 current will flow in this branch. So now you can see here I2 will come here and I1 minus I2 will come here. So what would be the current that will come here? This branch current plus this branch current. This is I1 minus I2 plus I2. So minus I2 plus I2 will get cancelled. I1 will remain. So that is how you can reduce one variable right away, so that you will be left with only two currents, I1 and I2. But if they specify find the branch currents, then you have to tell what is I1, what is I2, then what is I1 minus I2. I1 minus I2 is this branch current. Okay, I1 is this branch current and I2 is this branch current. So in this particular example, you can see here all the marks are nodes are marked A, B, C, D, E, F. Okay. Then direction of tracing. This is the direction of tracing. Now the current I1 comes here, I2 goes here, and this is I3. So I have taken two different values. So this is for the just understanding. You can solve using this method. Once you are comfortable with this, you can replace this I3 with, you can apply Ohm's law here, Kirchhoff's current law here to node B. Incoming, sum of incoming currents is equal to sum of outgoing currents. That is what? I1 is equal to I2 plus I3. And if you rewrite the equation, I3 is equal to I1 minus I2. I1 minus I2. Instead of writing I3, you can write I1 minus I2. Whenever you are doing the calculation here in this branch, you have to take it as I1 minus I2. So first we will do it using the I3 itself. Okay. Apply KCL to node B. This is the node B. I1 incoming current is equal to sum of outgoing currents. Therefore, I1 is equal to I2 plus I3. This is the first equation that I get. Then apply KVL to loop A, B, E, F, A. Okay. A, B, E, F, A. We are going to apply the KVL. So we will start from the node A. We come across this register. The direction of current is in this direction, and the direction of the tracing is also in the same direction. And what is the current that is flowing in this register? I1. What would be the voltage drop? 2 into I1. And what would be the voltage drop sign? Because both the direction of tracing and direction of current are same, plus 2I1. So if you go to the next, so this is the first, plus 2I1. And next, then you go to this branch, because we are going to do A, B, E, F, A. Then you are going to come in this direction. You are coming and hitting the positive plate of a EMF source. So you are going to take this value as a positive, plus 10. You can see this is plus 10. Next, you come across this. You are having a resistor here. So this is the direction of tracing and this is the direction of the current. So voltage drop is positive and the current flowing in this branch is I3. Voltage drop is plus 5 into I3. You can see plus 5I3. And you will come back to node E, F. Now you are coming and hitting the negative plate of a EMF source. This value will be taken as minus value, that is minus 30. You can see minus 30. And you come back to the node A. We are done with all the components in the loop. Then you will say equals to 0. And just do the simplification if possible. 2I1 plus 5I3. 10 minus 30 is 20. Minus 20. So minus 20 is taken on the right side, 20. So this is the second equation. This is first equation, second equation. Now apply KVL to loop B, C, D, E, B. Okay, B, C, D, E, B. You can choose to apply the KVL to this loop, or if you want to apply to this loop, that is also fine. Okay, and anything is fine. You will get the answer. So if you apply to this loop, we start from the node B. Okay, B, C, D, E, B. Applying the KVL, we start with node B. So first we come across the 3 ohm resistor. Direction of the current is this way and direction of tracing is this way. So positive voltage drop. And what is the current that is flowing in this resistor? I2. So voltage drop is plus 3 into I2. You can see plus 3I2. Then you come to the node C and come across the EMF source. You come across the positive plate of the EMF source. So you will take this value as plus 5. You can see plus 5. Then you continue the tracing. Now we come across another resistor. So what is the current that is flowing here? Same, in this branch I2 current will flow, right? I2. And the direction of the current and direction of tracing is exactly same. So this voltage drop is plus 4I2. Plus 4I2. Next, you will continue like this. Now you can see the direction of the tracing and the direction of the current. They are opposite. And what is the current that is flowing in this branch? I3. So this voltage drop is going to be a negative voltage drop. So what is the voltage drop? Minus 5 into I3. That you are going to write. Minus 5I3. Minus 5I3. Then you will continue. Now you are coming across a negative plate of a EMF source. You take this value as minus 10. You can see minus 10. Then we come back to the node B. Now all the components are done. You will say equals to 0. Then you can simplify this equation. 3 plus 4I2, 7I2, minus 5I3, 5 minus 10 minus 5. 5 is taken on the right hand side. So this is the equation. Now we have 3 unknowns and 3 equations. So this is the first equation, second equation, third equation. So you know how to simplify. Either you can use the substitution method or you can use the Cramer's rule, whichever is easy for you. And also in your Calc C, directly you can enter these equations. Just look out for the manual, and you can directly enter these values, and you will directly get the values in the calculator. But what I would suggest is you can use your calci for verification purpose, but do the calculation manually. Use any method you want to use, and you can solve these three equations for the three unknowns, and you will get the value for I1, I2, and I3. So how it is done here is replace I1 value from equation 1 into 2. So we will replace the I1 value into equation 2. So if I1 is what, I2 plus I3, if I replace I1 value, this will become in terms of I2, I3, and this equation is also in terms of I2 and I3. So I will be left with only two equations and two unknowns we can easily find out. So if you do that, we replaced here, the new equation I get is 2I2 plus 7I3 is equal to 20. Now equation 3 and equation 4, I have two equations and two unknowns in terms of I2 and I3. If I solve for this 2, here I have used the method where I will make these values exactly the same, these values same. So I will multiply the first equation with 7, so that I will get here 35 I3 minus 35 I3. Second equation I will multiply with the 5. So 5 into 7, 35 I3. When I add the two equations, this will get cancelled. Okay, this is a mathematics, just a mathematics. So if I multiplied this, what I get, 49 I2 minus 35 I3 is equal to 35. And if I multiply 5 to this equation, 10 I2 plus 35 I3 is equal to 100. So you can add the left hand side values and right hand side values. On the left hand side, you will get rid of the I3. What remains is 49 I2 plus 10 I2, it will be 59 I2, and these two value get added, 135. Therefore I2 is equal to what, 135 divided by 59. We get the answer for the I2 as 2.288 amperes, and answer for the I3. So in equation 4 you can substitute the value of I2. So what is the equation 4? Okay, I2 already we got. So what would be the I2 value, I3 value, 20 minus 2 I2. I2 is known, divided by 7. That is what is done here. 20 minus 2 I2 divided by 7. If you do this calculation, you get the I3 value as 2.203 amperes. And from the first equation we already know I1 is equal to I2 plus I3. So if we add here I1 value, we get it as 4.491 amperes. Now, what you can do is, now you understood how we solve this particular problem. Now you can go back to the same equation, okay, same circuit, and instead of taking I3, I want as a homework or as a practice, you take, instead of I3, you directly take this current as I1 minus I2. Okay, so this is I1, this is I2, then this would be I1 minus I2. So you will see how much calculation will get reduced. Okay, so you can take this particular problem and you are going to solve it now. Okay, we have the this particular circuit is given, find the currents in the below circuit. When they say find the currents in the below circuits, you have to find all the branch currents. Okay, for simplicity, all of us will follow the same convention. This one is, first we are going to mark the nodes. Let me go to the next slide so that we will have the same convention here. Okay, so this is A, this is B, C, D, E, F, G, H. Okay, and direction of tracing is same, clockwise. The currents I1, okay, and you take this as I2 and take this as I1 minus I2. Take this current as I3 and this current as uh, uh, I2 minus I3. This would be I2 minus I3. Once again, this current is I1, this current is I2, and this current is going to be I1 minus I2. Then this current is going to be I3, and this current is going to be I2 minus I3. Please take in that way. Okay, then you can try to solve it. So this will get very complicated if you take like this. We have 5 branch currents here, but we can eliminate 2 branch currents using the KCL. If we apply the KCL at node B and C, we'll get rid of 2 unknowns. So that's why equations will simplify. Please work on that. Note down the circuit diagram. And this is 14 volt and this is 5 volt source.